So this circular motion then, let's consider this point moving around in a circle anti-clockwise, starting time 0 on the x-axis here. So it starts here. We'll consider what happens, how it affects things when it doesn't start at 0. But assume for now that it does. So at time 0 it starts there, and then it moves around here in an anti-clockwise fashion. So after a time t, it will have reached here where we put the dot. You can also consider it as being a rotating phasor or vector. And so when you talk about AC theory and things like that, we often talk about some vector line. So that's what this red line represents, rotating round anti-clockwise. And we're considering a point at the tip of this thing as it goes round the circle, so the end of the vector line. And what we want to do is consider describing this motion. So the first thing we need to do is define a few things. So if we call the angle in the middle there theta, and we call the rate at which this thing rotates round the angular velocity. So it has an analogy with linear velocity, same sort of sense. Linear velocity is the distance something travels in meters divided by the time it takes. The angular velocity is the angle that this thing sweeps divided by the time it takes. So the rate at which it sweeps around this circle, we could consider it to be that omega equals, therefore, omega is the symbol we use for angular velocity, by the way, omega. And that symbol there, omega, part of the Greek alphabet. So just as linear velocity v equals distance over time, and we tend to use s for distance, displacement, omega, angular velocity, is the angle over time. So there's a direct relationship between angular velocity and linear velocity in their sense. So if we talk about circular motion, we talk about angular velocity. V linear velocity, yeah. And the units, we measure linear velocity in meters per second, and we measure angular velocity in radians per second. So we need to define what we mean by a radian. So a radian is something that was defined to try and describe literally how far round the circle we've gone. So if we consider this arc length from there to there as part of a circle, so this is the arc length, then if the distance you travel around in this circle is equal to the radius of the circle, so r represents the radius, then we say we travel 1 radian. So that's the definition of a radian. This angle here is 1 radian. So instead of dividing our circle into an arbitrary number of degrees, 360, we say, okay, let's measure this angle in terms of the radius of the circle. So if I've gone round 1 radius, then I've gone round 1 radian in degrees. And if you think about it, if the radius gets bigger, if I make this circle bigger, then that means that the radius is going to be bigger, so the arc length will be bigger, and in fact the proportion is exactly the same. So it doesn't matter how big or small a circle is, the actual angle that's subtended is always the same, and so that's defined as 1 radian. So it's used because it gives you an actual distance moved around a circle. So that's why we use the radian in terms of angular velocity, because it gives you a proportion of the circle that's been described. Knowing what the circumference of a circle is, the circumference of a circle is 2 pi r. So 1 radian is 1 radius around the circle. So if I multiply that by 2 pi, I've gone round the complete term. So therefore, there are 2 pi lots of radians in the complete term, as we were saying this morning. So therefore, the 2 pi radians is a complete turn. So we've got these radians that we measure now, not degrees, radians. And when we're measuring angular velocities, we exclusively use radians for angle measure, not degrees. Okay, so we've got some definitions now. We've got angular velocity that we use to describe the rate at which this thing goes round. And it's a measure of what angle has been swept out divided by the time it's taken, the amount of angle per second. And this angle, theta, is measured in radians. And there are 2 pi radians in the complete turn. We can come up with a few more terms that or equations that are useful. For example, if I want to describe the total angular distance travelled by this thing, then it's going to be 2 pi radians, which is 1 complete turn, multiplied by the number of turns it manages to do in a second, if you think about it. The angular velocity, which we're talking about here, omega, is the angle, 2 pi, or complete turn, multiplied by the number of turns in a second. And the number of turns in a second is the frequency. So if, say, it goes around 1 complete turn in a second, frequency of 1, then we would say the angular velocity is 2 pi radians per second. If the frequency is 2 lots of 2 pi, 4 pi radians per second. So you multiply the frequency by 2 pi to get the angular velocity. So that gives us a formula. If we define the frequency as the number of turns per second, number of complete turns per second, which is what we do, then we've got that omega, the angular velocity, is 2 pi times the frequency. And that's a little equation we use a lot that relates the frequency of rotation with the angular velocity. And we used that this morning when we were thinking about those torsion equations. So we can also come up with another relationship that relates the linear velocity v and the angular velocity omega. Omega r. So if I know the angular velocity of something, I just multiply that by the radius of curvature of the thing that's rotating. It gives me the linear speed of the thing that's moving around in terms of distance over time, meters per second. Useful if we're trying to relate situations where I've got some rotating drum, for example, and off that is being extruded some wire or something like that. What's the relationship between the linear speed of this thing, this belt or whatever it is we're concerned with, and the angular velocity of the drum that's rotating? The relationship is just the linear speed equals the angular velocity times the radius of the circle of the drum that's rotating. Okay, so what have we got? Some definitions to do with circles. We now know what angular velocity means and the symbol that's used for it, omega. It's the rate at which angle is swept round. There are 2 concepts that we talk about, the linear speed and the angular velocity, or linear velocity and angular velocity, and we now know there's a relationship between the 2, and it's a very straightforward relationship. We also know that we can describe this angular velocity, omega, in terms of the frequency from what we know about the circle. It's just 2 pi if we're measuring the angle in radians, which we do, times the frequency, and that gives us the angular velocity. Useful formulae. What I want to talk about now, though, is the relationship of this with this wave function, wave functions, and in particular the sine wave function. So let's look back at our circle again, and I've got here a YouTube video, and these notes, if you copy the notes afterwards, if you go to this site, copy this site in, then you can get to this link. And it will help us to describe what happens as this thing rotates around. So let's again put on our axes. And consider this thing rotating around anti-clockwise with an angular velocity omega. Let's consider now what happens over time as this point here moves around this circle. We're often interested in not the actual motion in the circle, but the effects of this motion in a particular direction. So if at time 0 it starts here, as we said, we're going to initially start by considering it starting here, we might be interested in how far up the y-axis has it moved. Well, at time 0 it's not moved, it's here. But as it comes round to this point, say, we could then say it's moved this distance up the y-axis. Then it moves round to here, at which point it's moved this distance up the y-axis. And we can plot a graph of what happens up the y-axis as it moves along, as time goes by. So x is often time. So this is often time. So as time goes by, what's happening in the y-plane as this thing rotates round? And if we plot a graph of it, we see we get this familiar sine wave. And let's go to this little YouTube clip, this clip here, that if you want to have a look at, there it is. If I just go to here, this is the YouTube clip. Probably, if I'm clever, I can expand it out. Yeah. Hit play. And you see that as time goes by, you see this thing moving around, and it's tracing, this point is tracing how far up and down the y-axis it's gone. So now it's reached the maximum negative point position on the y-axis, comes back up, y is getting smaller and smaller, until at this point there it's gone a complete turn. So, okay, I want to repeat it. How do I go back? Yeah, there we go. Just pause it a sec. Let's go back to the beginning. Can we play around with it? Yes, we can. Okay. I want to go back to the start. How do I do that? Doesn't let me, is it? Yeah. Okay, so at time 0, it's starting here at D and then rotating round. So if I let it roll and then try and stop it at the top, it's now gone through 90 degrees. But think of it in terms of radians. If that's 2 pi radians is a complete turn, then half a turn will be pi radians. A quarter of a turn, 90 degrees, is pi over 2. So after pi over 2 radians, it's reached the maximum value up the y-axis. And then we allow it to rotate a bit further. After pi radians, at half a turn, it's gone to 0 again, and then goes negative. And so after 3 pi over 2, 3 halves of pi, it will have reached a maximum again, and then one complete turn back to 0. And so the sine wave that we're familiar to seeing actually comes from a rotating vector where we're considering only what happens in the y direction. We're only interested often in what's going on in the y direction. So if you think about this thing moving up and down in the y-axis, and then we consider it, and this is what an oscilloscope does, it allows this trace to move not only up and down but also sideways. You then get this familiar sine wave. Yeah. So that's where the sine wave comes from. Less common, and so I'm not going to go into any great detail, you can also plot a graph of what happens along the x-axis as time goes by. So at time 0, when we're here, we would say it's actually the maximum distance along the x-axis. So it starts at the maximum value, and then as time goes by and we move round, it's moving less and less distance along the x-axis, and we actually end up with a same sort of shape, but it's out of phase with the sine wave, and we get what's called a cosine wave. And the tangent wave considers what happens to the opposite divided by the adjacent, because if you compare this with the sine, cosine and tangent ratios, if that's theta, and that's the opposite, the adjacent and the hypotenuse, then we've got the sine, cosine and tangent ratios that we're familiar with. Okay? Sine theta is the opposite over the hypotenuse. Cosine theta is the adjacent over the hypotenuse. Tan theta is the opposite over the adjacent. So if we try a few values now in our calculator, we can see how it works. So in your calculator, make sure you're in radians. To go to radians on the usual calculator, hit shift mode, and then it gives you an option to hit number 4, I think it is, for radians. Find the sine of 0. Answer 0. Does that fit with our picture? Yes, because at time 0 we're saying it starts at 0 here. Cosine of 0. 1. In other words, it's got its maximum distance along the x-axis when angle 0. What would you predict the cosine of pi over 2 to be? Pi over 2, remember, is here. So what would the cosine of pi over 2 be? 0. Try it. Okay. Sine of pi over 2. So sine of pi over 2 is 1. So that's telling us something about the length of this vector that's rotating round in a circle. What can we say the length of this vector is? No, because when it reaches the top, it's at maximum value, so it must be 1. So on your calculator, all the sine and cosine values that it gives you is assuming that this is 1. So it's assuming the hypotenuse in this triangle here, the green triangle, is 1. If the hypotenuse is not 1, what do? We multiply by the length of that line, which is why, if we go to this function here, if I want to know what the opposite side is, I just multiply the hypotenuse by the sine of the angle. The sine of the angle tells me the length of this side, the distance up this y-axis for whatever angle we've got, assuming this is 1. So if I want to know what the length of this side is if this is not 1, I just multiply it by the length of that hypotenuse side. So the use of sine and cosine and tangent less commonly in engineering problems to do with structures comes from exactly this idea of something rotating round in a circle, and then this sine wave that we've just seen tells you what the values of the distances at the y-axis, in other words, the opposite side of the triangle, for all different angles, measured in radians or degrees. So that's the use of it. Tell me what the sine of 270 degrees will be without doing it on your calculator. Where will this spot be after 270 degrees? Right, so what's the sine? Minus 1. Somebody said, yeah. Because this, if this is plus 1, remember the length of this vector is 1, so at this point it will be 1, at this point it will be minus 1. What's 270 degrees in radians? 3 pi over 2. Pi over 2, 2 pi over 2, or pi, 3 pi over 2, and so on. So we can use the calculator to predict certain values, and it will tell you the values if the length of this line is 1. Okay. So What I want you to do, because we're going to go downstairs now, is to investigate this function. I want you to investigate this sine function. But there are certain constants. We could multiply the sine by some number in front. If this is the x value, t, because time, it's often time, so t, we could multiply t by some number. And we could add something inside. So we can find the sine of t multiplied by some number and also have something added. And we can also multiply by a number in front. So that gives us all the possible options for how we can change this sine function. There are three constants we can add to the function: a, omega, and phi, as they're called. So this is, we know already, is omega. From what we've just been doing, there's a clue as to what omega is going to do. And phi is the name for that symbol there. It's a circle with a line drawn through it. I want you to use autograph, and I'll show you in a second how to get the function in there, to investigate the effect on this sine wave of changing the constant a's, omega, and phi. So if you can make a note of that. We'll talk about that. I'm going to allow you to investigate phi, and then you might be able to answer that question for yourself. That symbol is used for diameter, true, but it's this letter phi is part of the Greek alphabet, so yeah, used to represent diameter, but also used to represent something else in these wave functions. So let's look at autograph and see how we can put this function in. So I'll just get you going on it, and then we can go downstairs and you can get stuck in. So if I fire autograph, so once you've got autograph fired up, if I were to type in the equation y equals sine x, literally type in y equals sin x sine x, it will plot the function y equals sine x. There it is. Now, I would quite like to see it in radians, so it's in radians, so check the radians button, not the degrees button, it will give it to you in radians. Now if you hit the default scales, it's worth doing, because then it tells it to you in terms of pi. You can see straight away, if I look at this thing, let's just drag this menu over here so I can get the hand tool. You can see one cycle in terms of what we're looking at on that YouTube video. Look, starts at 0. After pi over 2 radians, it's reached the maximum value. After half a turn, which is pi, it's back down to 0 again. Then it goes negative, and one cycle, 2 pi radians, so one complete turn. Now we've got that sort of picture in there, we can then go back to this equation here and type in y equals a sine, and then bracket, bracket. The omega symbol isn't on there, so if we just use w to represent omega, omega x, plus the phi symbol is there, it's down here, look, there, okay, and then hit close bracket. Then that's going to affect the curve, and I want you to investigate what effects it's having and then try and come to some conclusions. Remember from last time we were talking about if you introduce constants, like we've introduced a, w, and phi, as soon as we introduce a constant, it will appear in this drop-down menu under the constant controller. So we've got three variables, three constants rather, a, phi, and w that we can change, and note what the effect on the curve is. Okay. So what I'd like you to do when we go downstairs is play around with these sine functions, and also look at that exercise for the power functions, and maybe try one or two in there. Okay. Any questions?